All right, so let's begin. Uh, so last class we introduced the Gibbs free energy, and this is in the context of stability criterion, things that allow us to say when a system or how a system will go towards equilibrium in a spontaneous or irreversible fashion. And what then happens in a very, very broad and general sense, thermodynamic sense, when you reach that stable equilibrium state. And in the case where you have constraints, and there are many constraints, the most practical constraints one can envision are when you can control temperature and volume, or temperature and pressure. And usually temperature and pressure are the things that are most convenient to control in the lab. And so we found that under conditions where you control uh, temperature and pressure, or they're fixed, there were many ways to say this. They're fixed, uh, they're statted in some way, right? Pressure stat, thermostat. Uh, so there's no dP in the system, and there's no dt in the system, or equivalently delta T and delta P. Under these conditions, we found that there's a thermodynamic function called G, the Gibbs free energy, which for the moment at constant n we'll say is only a function of temperature and pressure. And we define that as H minus Ts. And we know that H is equal to U plus PV. So we can actually write it this way. Okay. We also know that U minus Ts is equal to A. So we can write this as the Helmholtz free energy plus pressure times volume. And if I recall, we talked about A last class. And I think A was U minus Ts, which is the Helmholtz free energy, and that arises when you have constant temperature and volume. So there are various ways you can write the Gibbs free energy. They're all equivalent. Okay, so this is the definition. And you could also say that this is the definition just because of what we've defined earlier in terms of our thermodynamic potentials. So as a side note now, we have U, we have enthalpy, we have the Helmholtz free energy, and now we have the Gibbs free energy. And I reiterate that U is a function inherently of entropy and volume. H is a function now of entropy and pressure. A is a function of temperature and volume, and G is a function of temperature and pressure. Okay, so these are the inherent or natural variables or natural functions that these overarching thermodynamic potentials U, H, A, and G depend on. Okay. And this arises because we arrived at these expressions or these definitions, such as this, from the combination of the first and second laws, in the most general sense. Remember, all of these guys arose from the expression du plus p external dv minus t, well, it's p surroundings, TdS is less than or equal to 0. All of these guys originated from starting with that inequality, which is a combination of the first and second laws. Okay, starting with that, and then imposing certain constraints. Starting with the least practical, where we constrained S and V to have an isolated system, and then to the most practical, where we constrained temperature and pressure to get G. Okay, and so what I want to impress upon you at this point is that everything we've done so far can be traced back to the first law, in fact, and in first and second laws. So if you were to take time to look at any equation, for the most part, that you've been dealt in your courses, you can always trace it back almost to the first and second laws of thermodynamics. It's pretty amazing that you can do that. Okay, so we have this thing called G. Okay, so G is a function of temperature and pressure. The total differential the total derivative of G of temperature pressure is dG is equal to V dP minus S dt. Okay, so that's the total differential. And we know that for an irreversible or spontaneous process, dG is less than 0. Okay, G is minimized. Okay, for an irreversible or spontaneous process. Equivalently, this is called spontaneous. Okay, and at equilibrium, or when you reach a stable state, dG is equal to 0 at equilibrium. Okay, and again, these are all for conditions where pressure, temperature are constant. So all of these things have to be met for any of these things to make any sense. And then finally, since G is defined as H minus Ts, okay, and we can write then dG would be dH minus dTs. Okay, and if we have temperature constant, okay, dG is equal to dH minus Tds at constant temperature. And we see that if we have an irreversible process or a spontaneous process, okay, dG, which is less than 0, is a competition, okay, between H being minimized, H being minimized and S being maximized. Okay, it's a competition. And so in fact, if S is not maximized, if S entropy actually changes in the negative direction, meaning that, for instance, you have crystallization, i.e. or protein folding, both of which have, from the point of view of the protein or from the point of view of the solid, in the crystallization example, entropy decreases. Okay? So in that case, the enthalpy compensates for this decrease in entropy. And we see that the spontaneous formation of a solid or the spontaneous folding of a protein, in the absence of anything like chaperones or anything like that that actually help the protein fold, is governed by the interactions, the enthalpy. And so the enthalpy, which has this U component, is heavily dominated by interactions. And so you can think about this as, in the case of a protein folding, you have some chain. I'm just going to make this idea more explicit and transparent. And let's say this is a random chain of peptides. So it's a polypeptide, and all of these torsions are some random values. Okay, and now let's say that this thing folds, and I'm not going to, keep the number of beads the same, but let's say it folds into some conformation where, let's say you have a turn. Sometimes these are called hairpin turns in a protein. What happens is that these are governed by interactions. So, so in the case of the polymer in this state, all of the torsions are free to take on many, many, many different values. And so you have many, many different microstates. Okay, this thing is flopping around. And so without any constraints on the system, this thing can explore a lot of microstates. And so W is large. But once this thing folds into a conformation, let's say like this, maybe it's an active conformation, so the protein can perform some enzymatic process or is involved in some important physiological transformation. Now your torsions are locked, and so you don't have as many W's. You don't have as many microstates, and that arises from interactions, let's say, between these two polypeptides. Again, this is a very abstract notion, but these can be electrostatic or hydrogen bonding type interactions, and further nuanced interactions. So you see here that because of this, enthalpy decreases. So whenever you have favorable interactions in the system, U decreases, okay, your energy decreases, this potential energy decreases. And so in the case of protein folding, though, delta S or ds, so ds may be up, sorry. So ds may be less than 0, okay, in the context of this expression, okay, but what happens is that dH is also less than 0 because of the interactions, okay, driven by these interactions, and this dH term overpowers the ds term, right? So the minus TDS term, if ds is negative, would be a positive contribution to dG. But if that positive term is overpowered by the dH and the negativeness of the dH, overall dG would be negative, and you would have a spontaneous process occurring. Okay. The same thing happens for crystallization. From the point of view of the solid, you see that if you have crystallization, if you have a beaker of, let's say, water, and your solid is this red stuff, it's all dispersed, and then you have crystallization going on where now the solid forms a crystal, okay? Here what happens is that you gain enthalpy from the interactions of the molecule of the crystal, so they actually interact with themselves, so there's an H component that's negative, even though you would say now that you're going from a state where you have many microstates to one perhaps microstate or very few microstates, because we know that in a crystal everything is in a lattice, and so there's not too many different microstates. But what happens in the case of a crystal now is that if you had, let's say, an ion, which is a positively charged ion, in this case, you would have water molecules that are bound to it in the sense that now the O is oriented. And in effect, if you have solvated ions, what that does to the water molecules is, because of electrostatic interactions, the water molecules on average take on this orientation around the positive cation, in this case, and that essentially limits the number of microstates that the water can take, because now these waters have to solvate the ion, the cation in this case, and so their orientational degrees of freedom, or the orientational microstates, the various ways that they can be oriented, is now limited. But once you have crystallization occur, okay, the water is liberated, and now we can have, here's your ion in a crystal lattice. You know, I'm making the lattice bigger now. Plus all of these waters now, which can have random orientations, or more random than they were in the case of hydrating the cation. And so these are the microscopic, atomic, molecular level considerations for S and H that go into understanding processes where you can have changes in entropy that are negative, okay? But again, this would all have to occur at conditions of constant temperature and pressure. And so if you were to put this in a system that's isolated, this may not happen, okay? You would have to have some particular conditions of temperature and pressure. Okay, any questions? All right, so the next thing I want to consider, okay, so let me just stop here, and what we're going to, so I gave you the conditions for stability and criteria. We're going to use those conditions. And the next midterm goal is that I'm going to use all of this machinery that we're developing. There's a few more elements that we have to develop to derive for you the equilibrium constant, K equilibrium. And I know you've seen this K equilibrium constant using rate analysis or discussion of rate constants, right? You've looked at chemical reactions, and by starting with rate constants and rates, reaction rates, maybe used, for a reaction A, nu A plus nu B goes to nu C plus nu D. And you've seen, maybe you've seen the rate is equal to some rate constant times A concentration, B concentration raised to the stoichiometric coefficients, perhaps. I want to actually derive for you, and then you have this K equilibrium where you have concentrations. Actually, it's C and D, right? And then A and B, and then you might have some coefficients, exponents. I want to derive that for you based solely on thermodynamic considerations, which is really the fundamental way to do it. And in fact, what you haven't been told is that this guy, this rate, is really the child of thermodynamic analysis in terms of transformations in the context of probabilities. Okay, so at the end of the day, everything boils down to probabilities. Life is probabilistic. Okay. Anyway, that's something that's very, very deep, and we won't get into that, but that's where it comes from. And so that's the midterm goal now, to get to the equilibrium constant once we develop a few more tools in our bag of tools here. Okay, so let's move on. One of the first things I want to consider before too long is these things called Maxwell relations. Okay, so this is a bit of guidance as to where we're going. Okay, in the midterm here, midterm time frame. So the Maxwell relations are something that's useful because it allows us to access changes in these thermodynamic potentials that we've seen in terms of equations of state. Okay, so they're very useful. So let me just sort of start with G, and we'll look at the total differentials. So the total differential of G, which we have developed so far, is VdP minus SDT. So are there any questions, by the way, before I move on, or comments? All right. So we know that this is our total differential of G, and all of the things that appear in this equation are state functions. Okay, there's nothing that's path dependent here. So the power of these thermodynamic potentials and their differentials is that we can use them for any kind of process, whether it's reversible or irreversible, right? And that's very powerful. And because they're state functions, there's some relationships that hold between differentials and partial derivatives of all of the functions that you see here. So let's begin with the most obvious one. So starting with this expression, we know that the volume is a partial derivative. The volume is the partial of G, which is a function of temperature and pressure, with respect to pressure when we hold temperature constant. Okay. We also know that negative S is equal to the partial of G when we, with respect to T, when we hold pressure constant. Okay, so those things are obvious from the expression with the two arrows pointing to it. Okay, that's just from how total derivatives are. But now we can ask about second derivatives. Okay, we can ask about second partial derivatives because we have G depending on pressure and temperature. Okay, we have G depending on two variables, temperature and pressure. So in each one of these guys, we've only taken the partial derivative of G with respect to one of those variables. In the first case, we took the partial with respect to pressure. And in the second case, we took the partial with respect to temperature, holding the other variable constant in both cases. Now what we can do is, having taken the partial derivative, the first partial derivative of G with respect to one of those variables, we can take the second partial derivative with respect to the remaining variable that we held constant the first time. So in the case of V, which is the first partial derivative of G with respect to pressure, we can take now the second partial derivative with respect to temperature, because G depends on temperature as well, right? So what we can do is we can take the partial of V. I'm going to take the partial now of both sides of that expression with respect to temperature. So I can take the partial of V with respect to, let's see, I want to make
T.
sure that this, sorry?
Is it T?
T, yes, you're right. And what do I have to hold constant? The other variable, and that would have to be
P.
P, exactly. Right, so that's the left-hand side. And then on the right-hand side, I'm going to have now nomenclature that indicates partials, second partials. So let's take this slowly. What we're going to do now is take a partial with respect to t of what already was there. What was already there?
Partial G of T of P with respect to P of T, constant T.
Exactly. And since I'm taking now the partial with respect to t of that thing in the big parentheses, what is held constant? What do I have to put as a subscript?
Pressure.
Exactly. That's exactly right. So now I have this inequality here, okay? Or sorry, not inequality, this second derivative, this equality. Uh, now let's do the same for S, okay? Now we're gonna do the same for this guy. All right, now I'll just put this here. We'll take the partial, but in this case, what are we gonna take the partial derivative with respect to? When we take the second partial.
P. Or, I'm sorry, T.
Yeah, no, for the S. So we already took the partial of G with respect to, for this guy.
Oh, we took it for T.
Right.
So
Now we have to do with respect to,
P.
exactly. So let's do with respect to P on both sides. So the left hand is easy, right? That's just going to be minus partial of S with respect to P at constant.
T.
And then the right hand side is going to be the partial with respect to P, what's already there. And this will have to be at constant.
Constant T.
Right, exactly. Okay, so those are the two second order partial derivatives of G, and that's really all we can do because G depends on two variables. So there's only two partial derivatives. Sorry, you can only go up to second order in terms of the partial derivatives. Okay. Now it turns out that for things that are state functions, okay, these are called exact differentials, or things that are called state functions. That's why they're, again, another very special property for state functions. These are called exact, another way to call them is exact differentials. And again, this is a math thing, so I won't spend too much time on it. Okay. Purely mathematical, that's pure mathematics. It's an exact differential. And it turns out for these kinds of functions, these two partial second order derivatives are equal, okay? Which means then that this guy and this guy are equal. Okay? Because G is a state function. And this also holds for A, H, and U. But I'm using G as an example. So what this is telling me is that these second order derivatives, so let's write the equality of the second order derivative and then we'll see what that is. So what this is saying is the partial of T of partial of G okay, so that's this term right here. Okay, I use the right hand side. I just rewrote it and I'm going to equate it to the right hand side of this expression right here. Okay, that's going to be partial with respect to P of partial of G dt. Okay, so those two. So if you have a state function or an exact differential, this is the definition of what that means. Okay, G is our state function here, or exact differential, which means that the second order partial derivatives, when you have dt dp or dp dt, they're equal. Okay, and that's really all this is. What we've done here is it's the order in which we've taken the partial derivatives, really, if you take a look at it, right? So on the left, first we took it with respect to pressure, and then we took it with respect to T. And on the right, we first took it with respect to temperature, and then we took it with respect to pressure. And for this very special case of functions, class of functions, these two are independent of the order of partial differentiation, and they're equal. Okay. Now we know what these complicated kind of things are equal to based on these expressions up here, okay? So the guy on the left is equal to dV dt at constant pressure, okay? So I'm gonna write that now. So this is just equal to the partial of V with respect to T at constant pressure, and the guy on the right is equal to the negative partial of S with respect to P at constant T. And that's just equal to the partial of S with respect to P at constant T, okay? And so this is actually a very useful and powerful result. This is a Maxwell relation. I'm not talking about the electrodynamics, I'm talking about these are thermodynamic relations, and this is one example, and there are many Maxwell relations. These are given in your handbook. So this is one example of a Maxwell relation, because it relates these two temperature, pressure, volume, entropy to one another. And you see here, okay, that since we don't have an entropy meter, right, this may allow us to get changes in S if we knew or had measurements from which we can derive functions that would give us relationships between pressure, temperature, and volume. So let's think about this, right? So now what we've done here is, starting from the first and second laws, right? Starting with the first and second laws, we came at this very general inequality, remember? And from that inequality, when we let temperature and pressure be constrained, we came up with this thing called G. And we know now that the G has a different total differential, okay? And based on the fact that G is a state function, because all of the things that G depends on are state functions, we have these relationships between partial derivatives. So in fact, okay, this result is purely a thermodynamic result. I didn't have to resort to anything such as dq is cpdt or anything like that, right? This is pure unadulterated thermodynamics, right? It's the first and second laws, okay? It's purely fundamental. And so what this allows us to do now, because we don't have things like an entropy meter, is we can isolate the differential of S under particular conditions, okay? So we have on the right-hand side ds dp at constant T, okay? So what we can do is, now let's say T is constant, right? S perhaps can depend on many variables. And in this case, if we were to say, well, all right, it's a function of pressure and temperature when N is constant, let me just say that ds, okay, I'm going to write this, is equal to the partial of V with respect to T at constant P times dP. And this is going to be something that is at constant T, okay? So do you see what I did here? All I did was multiply this by dP. Okay. Any questions on that? Any questions on that? Okay. Well, that's great, because now, purely from a thermodynamic analysis, first and second laws, I can actually compute changes in entropy at constant temperature, because I have at my disposal information about how volume changes with temperature at constant pressure. I have this guy, and where do you think that that information might come from?
Real gas, or PV equals nRT.
Right, and so what are those things called? you're right. And so the most general way to,
Oh, ideal gas law.
okay, but if it's not ideal,
Observables.
these are observables, but when we put them together into a mathematical model, that thing is called
Equation of state.
equation of state, exactly. Right? So again, so now we're going back and connecting all these little ideas that these equations of state, yeah, they are coming from observables. That's exactly right. But once we apply our mathematical intuitions and knowledge, we create models that are called equations of state. And this is the power of equations of state. The ideal gas law is really an equation of state. It's just one example of an equation of state. And so this now ties in without having to presuppose anything from the beginning, starting from the first and second laws and a whole bunch of careful analysis. We see that, oh, we can actually compute changes in something called entropy, which we don't have a meter for. There's nothing that we can stick into a system and read out S's value of 10 joules per K or something like that, right? We have to go the hard way, right? It's like you can either touch your nose, in my case, my big nose this way, or you can touch it this way. Well, in this case, we have to touch it this way. And the thing that allows us to do that is the equation of state, right? And so if we had an equation of state, we could compute the partial of volume with respect to temperature at constant pressure. And as an example, yeah, we could use the ideal gas, and that's something that I can, we all know that we can use. So this is the ideal gas equation of state. We've seen that many, many times. And we can take volume, which is nRT over P. Okay. And we know that if we wanted to take the partial of V with respect to temperature at constant P, that's just nR over P, right? Am I correct? Yeah, I believe so. Okay, so once we have that, we can actually stick this result into our expression here. So now I have ds at constant temperature is equal to nR 1 over P times dP. Okay, and now I have to say that this is for an ideal gas.
Is the ds supposed to be negative? Because you had the at top.
Oh, you are right. Thank you, sir. Exactly. Good job. Yeah, it's negative. You are exactly right. So the negative there, and so I have to have a negative here, right? Yeah. Thanks, Sheldon, right? Good.
Yeah. Good.
Thanks for pointing that out. So ds for this ideal gas case, as our example, this is an example, right? Is n minus nR 1 over PdP, which is just minus nR dP over P, and I can write that as minus nR d log P. D log P. So that's ds for an ideal gas at constant temperature. And so you see here how neatly we came to this result purely from thermodynamics. We had nothing else. And of course now it allowed, we needed an equation of state, but that's fine, because once you get to this point, you say, oh, I have V, temperature, pressure, and I know how they're related. I can do some experiments and I can figure out how they're related. Okay? So I can either come up with a mathematical model, or I could actually do this numerically. So I don't know if you've been, introduced to numerical methods, but in fact, you can solve differential equations using numerical methods. And I'll just say that, but I won't get into any details there. Okay, but that gives us a lot of confidence, and it makes you feel safe that purely from thermodynamics, you can come to something like this, and it's totally tied into experimental observation. Okay, something that is this abstract thing called entropy, for which there's no meter, is tied just magically and intimately to experimental observations. And these experimental observations are embodied in something called an equation of state, or you could do this just by using numerical methods. Okay, so once we have ds at constant T for an ideal gas, which is minus nr d log p. Okay, you can just integrate. I mean, now it's just a simple integration. It's so simple. And since pressure is a state function, as is S, log P is a state function, as is S. So delta S at constant T, if you're going from, which is equal to S at T2 minus S at T1, is going to be the integral. And I'll take the minus NR out because that's just a constant. And that's going to be the integral of d natural log of P from P1 to P2. Okay, as temperature changes. Sorry, so this is not going to be a, so what am I saying here? This is a boo-boo, right? T doesn't change, is that constant T? It's P. All right, because we were interested in the variation of S with respect to P here, right? That was, so sorry about that, just make sure I just misspoke. So this is S at P2 minus S at P1, which is the integral of minus NR, the integral minus NR times the integral from P1 to P2 of d log P, okay? And this delta S at constant T, which is S at P2 minus, I'm rushing and that's not good. S at P2 minus S at P1 is going to be minus NR. This is just going to be natural log of P2 minus natural log of P1. But we know that we can combine that as minus NR natural log of P2 over P1. Okay. And that's actually how we would compute this. And now if we wanted to compute this in terms of volumes, okay, because we know that volumes can change too, if pressure is changing, right? We know how to do this because for an ideal gas, P2 is equal to, what is that? nRT over V2, am I correct? And P1 is equal to nRT over V1, because in this case, temperature is constant, because temperature is constant, right? I think I'm right, P is equal to nRT over V, right? So what we can do is stick those relationships into this P2 over P1 ratio. So delta S at constant temperature is equal to minus NR natural log. P2 is nRT over V2, and P1, which is in the denominator, is equal to nRT, and the V1 comes on top. So that equals minus NR natural log. So the nRT and the nRT cancel in both cases, and we're left with V1 over V2. But now I'm just going to flip the V2 and the V1, and that's going to change that negative sign to a positive sign, NR natural log V2 over V1. So based on the Maxwell relations, we see here that at constant temperature, we can derive expressions for delta S at constant temperature in terms of the changes that are associated in volume or pressure, right? As long as we have an equation of state, or we have, or we know an appropriate numerical method that allows us just to use the experimental data to do the differentiation, or sorry, the integration. Okay, and that's called quadrature. For those of you who may be interested in fancy words, when we do numerical integration, it's called quadrature, okay, if you talk to a mathematician. So any questions on that? I think, we're getting into some very cool stuff now, and it all hinges on this very fundamental thermodynamics. I get excited about this stuff anyway. So any questions on that so far? Or comments? Thanks for pointing out my mistakes along the way. So now I was using G. Okay, so we use Gibbs. We can do the same thing using A. And what I would like to encourage and invite you all to do is to see if you can use the Helmholtz free energy, okay, and derive the same stuff that we did, starting with G, start with A and its total derivative, total differential, and see what you get, okay? And at the end of the day, what you'll be able to see is that that P that we had for G, since Gibbs is an inherent function of temperature and pressure, A is an inherent function of temperature and volume. So intuitively, you might think that, oh, if I use the Maxwell relations that come out of an analysis of A, the Helmholtz free energy, I should be able to get changes in entropy with respect to volume at constant temperature. Just as we have done using G, we were able to get changes in S at constant temperature with respect to pressure. Okay, so I'm not going to, I have confidence that you, oh, come on, please, what happened here? Okay, good. I thought technical difficulty. All right, so start with dA. So A is the Helmholtz free energy, and that's equal a function of temperature and volume. And we know that its total differential is minus P dV minus S dt. Okay, just as with in the case of G, we had VdP minus S dt. So that minus S dt term is the same, right? That's that temperature thing. But between A and G, the thing that varies is this term, right? And for G, it's VdP, and for A, it's minus PDV. And so that change will allow you to derive some other things. So I'm going to let you do that and work on that, okay? It's just a matter of sitting down and doing it. It's not that difficult, okay? Okay, so give it a shot, give it a crack. It's not that difficult. All right, any questions? I'm going to move on. No questions or comments? Okay. All right, we're making good progress here. So again, with the Maxwell relations, I just want to reemphasize that it's a way to connect changes in thermodynamic potentials, such as entropy, for which there are no meters. There are no machines that you can read out a value of S. We have to get through those indirectly. And the way we do that indirectly is by using equations of state that give us information and relate measurable things, temperature, volume, pressure, that we can then put together and manipulate so as to get changes in entropy. Okay, so that's the power of these things and the power of thermodynamics. Okay, and why do we care about entropy? Well, entropy is one of these things that's a guiding principle, right, for stability and spontaneity. Right, so we care about entropy in that sense. Okay, so if we want to know whether a process is going to occur under certain conditions, right, we want to know these guiding principles, and so we have to be able to calculate whether they're going to increase, decrease, or stay the same. Okay, and as we move along, I will show you how a lot of the equations that you've been shown arise from that. In particular, the equilibrium constant comes about from the fact that we minimize G. Okay. And that's really amazing. Okay, so let's move on. So moving towards this idea of the equilibrium constant, let's go now and talk about open systems. Okay, now we're going to talk about, any questions, comments? Okay, now what we're going to do is talk about open systems, and open systems are really useful for us as chemists because they allow N to change. Okay, now we're going to start talking about situations where the number of moles change, and that's important because that's what happens in a chemical reaction. The number of moles of a reactant change, and the number of moles of products change because one is being depleted and one is being created. Okay. So we'll talk about open systems now, where dN is no longer zero. dN is some finite value, okay? So dN is no longer zero. And if you have multi-component systems, and of course, we have multiple chemical reactants and multiple products, if we have multi-component system, then we would have to label each one of those number of moles N as I. We're going to label that as species I. And so dNi is not equal to zero. So the number of moles, the differential change in the number of moles of species I is not necessarily zero anymore. Okay. And so the last point I want to introduce before we quit is this thing called the chemical potential. And now we're really getting into the fancy stuff, right? Upper level course. This is really fancy, right? Chemical potential. Okay. This is where it's at. Okay. We talk about things, the chemical potential. And this is going to allow us to now treat systems where N is changing. Okay, and of course, this is very important for us as chemists. So and the way we'll do that is first address how G is going to be affected when we allow N to change in the system. And so we know that G now is going to be a function of temperature, pressure, and N. Okay, so let's say we're going to start with just one component. Okay, just to make things easy to see here. So for a one component system, we'll just have N. Okay, there's no N sub I, it's not multi-component. So in this case, G is a function of temperature, pressure, and the number of moles of whatever you may have. And we're going to write the total differential, and you've seen this already, right? It's going to be very simple. The partial of G with respect to pressure, temperature, G is a function of temperature, pressure, and first, we'll take the partial with respect to temperature, but now we have to hold pressure and N constant because now we have G depending on three things. So this first term is partial of G with respect to T at constant pressure and N. Then we put a dt there. Then, I have the next term, which is going to be a partial with respect to P. This time I hold T and N constant, and then I multiply it by dp. And then now I'm going to have one more term because I know N can change. So it's going to be the partial of G with respect to N. And now we see how we're going to let G change as N changes in this open system where now the moles don't have to be constrained to be constant. That partial with respect to N has to be taken at constant temperature and pressure. That's something that we cannot run away from. And then we multiply it by dN, which is the differential change in the number of moles of the system. Okay. We know from above that the first partial, the partial of G with respect to T at constant pressure and N is just minus S. Okay. So this guy is just minus S. We already saw this. This guy is just V. Okay, you can go back into your notes and check. That's just V. And this new guy that we've introduced, right, our really cool friend, is this guy. And this guy is the chemical potential. And we denoted in this case, this is the single component, just mu. This is the Greek letter mu. Okay, and it's a function of temperature and pressure. Okay, and that's defined as partial of G with respect to N at constant temperature and pressure. And this is for a single component. We'll do multi-component next time. For a single component. And this, my friends, is the chemical potential defined in the most general way. Okay, it's defined in the most general way as a partial of G with respect to N. And you'll see that, in fact, we can define chemical potentials with respect to any of our thermodynamic potentials, U, H, A, G. But it turns out, of course, that G and A are the most practical because they're related to temperature and pressure. Okay, and I'll say, so we're going to build on this. We're going to make it a little bit, we're going to do a lot more things with this thing called the chemical potential, starting with expanding it to multi-component systems during our next lecture. Okay, so let me so for a single component system, then dg, this last thing becomes v dp minus s dt plus mu dn. Okay, so now all we've done is add this extra term, and I've defined that extra term as the partial of G with respect to n. And that should not be a surprise now because everyone knows what a total differential is for a function that depends on any number of variables. It's just this summation of partial derivatives and multiplied by those differential changes. All right, I really get excited talking about this stuff, as you can tell. So I'm going to stop. Any questions, comments? Okay, we will continue on Friday. I wish you happy rest of the week. And thank you for your participation and corrections to my lecturing today. Very much appreciated. Okay? I will
Thank
end the
you.
meeting. Okay, thank you all.
Have a nice day.
Thank you.